Hello guys, in this video lecture we will study an example of a non-Hausdorff one-dimensional topological manifold which is a line with the two origins. So let me remind you first what is a topological manifold of dimension n. So a topological manifold of dimension n is simply a topological space. Let me show it. Although it may not look like this as I have written here, but let us consider like this. So if we say that this is a topological manifold of dimension n, if around each point we have a neighborhood, first of all it should be a topological space. This set should be a topological space, and we impose further condition. Although that is not necessary, we demand that it should be Hausdorff also. But in this example we will study that Hausdorffness is not necessary condition for a space, topological space, to be a topological manifold. We also demand that it is Hausdorff. Later on we will show that this is not the necessary condition. So topological manifold of dimension is simply a topological space which is Hausdorff. Also around each point P of M, for each P belonging to M, which is our manifold, we have a neighborhood U. We have a neighborhood U which I have shown here by dotted. This should be homeomorphic to Rn, subset of Rn. This should be homeomorphic. This U should be homeomorphic to some subset of Rn or Rn. This should be homeomorphic to a subset of Rn. But in this example we will show that the Hausdorff condition is not necessary for a topological manifold to be a manifold. Hausdorff is not necessary. Hausdorffness is not necessary. So let us show this. It is known as line with the two origins. Line with the two origins. That is, we simply take the real line, delete the origin from it, and put the 2 points above and below it. Line with two origins. That is, we simply delete the origin from our real line R and put a point here. Let us suppose it is P, and let us suppose just below it is our point minus P. Let me denote this set by S. Let this be, or let me denote it by M. We will show that this is a topological manifold of dimension 1 which is not Hausdorff. So first this is a set, so we have to define first a topology on it. That is, we have to topologize this set with some topology. Then we will show that topology is not Hausdorff, and also we will show that locally this M is a is homeomorphic. For each point we have a neighborhood which is homeomorphic to a subset of R. So let us first define a topology on this line with two origins on this set M. So how we will define this topology? We will simply, this is our line with the two origins. Here this is P, here this is minus P. We will simply, for any point here which is not P or minus P, we will simply choose the interval. That is, let us suppose this is X. We will simply choose our interval in our basis. That is, B be the set of all intervals like this, but this should not be our P or minus P. We will add to this interval, these types of intervals, if we choose a neighborhood around P, then around this point P, if we choose a neighborhood that is a basis point, it should also include these points as well, but excluding minus P. It should not include minus P. That is the set. Let us suppose this is some minus A here, this is some A. Another set we choose in our basis, let it be minus A 0 union singleton P 0 A. This is this is our another set in the basis. First we choose all the intervals of the type AB, but that interval should not contain P or minus P. For P and minus P we choose different types of intervals. That is this interval. For P we choose an interval or its neighborhood to be minus A 0 union P 0 A. Then for minus P, similarly we will choose some minus B like this. For minus B we will choose minus B 0 union minus P union 0 B. Let me write this interval here, that is, it is minus B 0 union minus P union 0 B. This interval is written here. So we choose this set and we conclude that this is a basis for this topology. Then with this basis we will generate the topology for this line with the two origins, and we will show that this is not Hausdorff, and also we will show that this is locally homeomorphic to R, this line with the two origins. First we have shown that this is a basis for this for the topology. We will show that this collection is a basis for this set. So the two conditions for the basis, you know that first condition is around each x belonging to X we should have a neighborhood from this collection from B. We should have a set from B. For each point x belonging to M we should have a neighborhood or a set from this collection B. Also second condition is if any x belongs to some B1 intersection B2, which are the members of basis B for this collection. We haven't yet showed that this is a basis. I am only reminding you the conditions for the basis. There should exist another basis member B3 such that x belongs to B3 which is contained in B1 intersection B2. That is, if some point belongs to the intersection of two basis members, let this be B1 and let this be B2, we should have another basis member B3 which contains that point and which contains this point and is contained in their intersection. That is, it should be contained in this portion, which is clear from the figure. So we have to show first that this collection, this is a basis for this set. So if we draw our set here, which is our M, and this is our some point P, and below it is simply minus P. Now you can simply by observing around each point here, let us suppose which does not contain P, you can simply choose this interval, which is clear. We can simply choose, because this is a simply real line R, we can choose this interval which is clearly the basis member, which is the member of B. And for this P we can simply choose this in this set, which is clearly also basis member of the member of the basis B. This in this set, that is, let it be some minus A, that it be this A, some A is some positive real number. The set, that is minus A 0 union P union 0 A, which is clearly a member of our B. Similarly, you can choose for this minus P, you can similarly choose the same interval. Hence, for every x belonging to our line with the two origins, that is the set M, we have a basis member from this collection. Also, now we have to show the intersection property. Also, this is our P, this is our minus P. It is clear that if some point belongs to the intersection of two members of a basis member, then this is also a member of B. Clearly, because it looks like the interval, and around P here and minus P here. Now P cannot belong to for P, if we choose two different intervals, if we choose, let us suppose for P, if we choose, let us suppose this minus A here and A here, this one interval, and another interval like here minus B for some A and B positive real numbers. These are the two neighborhoods which contain the point P. We can easily, from the observation, it is clear that we can choose these two, we can choose the intersection to be minus B 0 union P union 0B, which is clear from the figure. You can choose this interval which is contained in the intersection of these two basis members. Hence, around any point we got a member from this collection B, and if there is some point which is in the intersection of both these intervals, these basis members, then there exists another basis member which is contained in the, which contains that point and is also contained in the intersection of both. Now we will show that this is not a Hausdorff. This topology generated by basis, this basis is not a Hausdorff topology. For that, we will simply choose this point P. Now we will show that this topology is not Hausdorff. Let me remind you first of the definition of Hausdorff. For Hausdorffness, we simply choose two distinct elements, x and y, and for every distinct pair of the elements, we should have distinct disjoint neighborhoods. If we can do this for every pair of distinct points, that is, we can choose two different neighborhoods, at least one around x and at least one around y, such that whose intersection is phi, that is u intersection v is phi, then we say that this is a Hausdorff topological space. So we will show that this topology generated by this basis is not a Hausdorff. So let us show. This is our set M. Here is our point P. Here is our point minus P. Now, if we choose these two points, that is P and minus P, clearly P and minus P are not equal. Now, we have to construct at least one neighborhood around P and one neighborhood around minus P, such that they should be disjoint. But the neighborhood around P will always look like this. That is, it will look like minus A, and the neighborhood around minus P will always look like, either you can choose some bigger point B here, that is, you can choose B greater than A, or you can choose B smaller than A. You can choose this neighborhood, that is, let me denote it by C. These are the two choices for minus P. It is, we can have a neighborhood which is greater than this neighborhood, we can choose smaller, but in both cases it is clear from the figure that intersection is not phi. It is clear that if we choose our neighborhood to be this one, then clearly intersection is not phi, because this smaller neighborhood will always be in the intersection. Or if we choose the smaller neighborhood, then this smaller will be in both. Hence we can't choose any neighborhood, disjoint neighborhoods around P and minus P whose intersection is phi. Hence this topology is not Hausdorff. Now we will show that this is locally homeomorphic to R. So let us now define homeomorphisms. So this is our set P, this is our minus P point D. Now we have to show that this is locally homeomorphic to R. So you can simply project down it onto R simply. This is our R, here is the origin 0. Now you can simply define phi by projecting all these pointers here and this point P onto 0, except this minus P. We will choose a neighborhood around P in this M, and we will show that that is homeomorphic to R, and also we will choose a neighborhood around minus P that will also show that it is homeomorphic to R. That will cover our whole set M. Therefore phi is simply then defined by our mapping. Phi will be simply, we will send every point here onto itself, that is it will be simply x for x not equal to P, and it will be simply 0 if x is equal to P. Now we have to show that this phi is homeomorphism, that is it is 1 1, it is onto it is continuous, and its inverse is also continuous. 1 1, it is clear from the figure that this is 1 1, because each point gets projected by natural projection to a unique point. Distinct pointers get mapped to distinct pointers, and P will get mapped to 0. Therefore it is 1 1 as well as onto. It is clear from the figure. Now we will prove that this phi is continuous. Phi is continuous. That is, we have to show that this phi of x defined by x for x not equal to P. Phi is defined from our set. Phi was defined from our set. Let me denote our set was M, but deleted minus P. Minus P is not included into R. This is 0 if x is equal to P. Now we will show that this phi is continuous. That is, and for R we choose the usual topology. For R we choose tau usual. We have to show that every open set has an inverse image which is open here under phi, which will simply show that phi is continuous. So now any open set here in the usual topology will look like, let me prove it graphically. It will be clear from the graph of this function. Let me prove it clearly. That let us denote this set our, this is our set M minus P. This is the neighborhood of P, and this is our R. Now every point here gets mapped to this, and P gets simply mapped to 0. This is our origin 0. Now we have to prove that every open interval or open set in R with the usual topology has an inverse image which is open in this topology, in the topology. So if we choose a neighborhood around any point here or any open set, it will clearly get mapped to this, which is clearly open in our set M minus P. Now if we have a neighborhood which will get which contains 0, that is if we have a neighborhood around 0 which is an open set, this is an open set, its inverse image will look like this. Inverse image of this, let it be minus a. Its inverse image will clearly look like phi inverse of minus a will clearly be minus a0 union p union 0a, which is clearly open in our topology on which we defined on this set M, as it was the basis member, and you know that basis members are always open. Therefore inverse image of this set is open as well. Therefore only two types of intervals are possible here. All different other intervals will look like the same. This is an interval and this is an interval. Their corresponding images will be same here. Therefore they are open as well. Therefore phi is a continuous mapping. Phi is continuous. Now we have to prove that phi inverse is also continuous. But phi inverse will be a map from R into M minus P. Phi inverse will be simply mapping from R into P. Let us also show that this is also continuous. So we have to prove that every open set here has an inverse image which is open in R. So phi inverse will be mapping from R. This is 0. This is simply R with the usual topology, and this is our set. This is our set M minus P. So by inverse mapping, every point will get mapped to itself and 0 will get mapped to simply P. Now we have to show that inverse images of the open sets are open in R. So if you choose any open set here, it will simply get mapped to here. This set will get mapped to here, which is clearly open in R. Now if we choose some open set around P, open set around P will look like this. This is our P here, and open set around P will look like this, containing P, and that will simply get mapped to this by phi inverse, which is also open in R, which is clear from the figure. Therefore phi inverse is also open as well. Phi inverse is open as well. Continuous. Phi inverse is continuous as well. Therefore phi is a homeomorphism. Phi is a homeo. Now we have to show that since this neighborhood of P does not cover all of our set M, we have to construct another homeomorphism. That is, we only covered this much portion from our set M. Now we have to choose the neighborhood around minus P, which we will show that that is also homeomorphic to R. I think the procedure is same for minus P also. You will map from this is our R. You will map this point to this point to this, and minus P to 0 origin, and you will simply delete this point, and then that set is clearly also homeomorphic to R as well. Therefore the atlas we got for our topological manifold is simply M minus P comma, let me denote first homeomorphism by phi 1 union M P comma, let me denote the second homeomorphism which you will describe yourself, which is the clear copy of what I did in the first example. This is a chart. This is also another chart for our manifold, and clearly their union is an atlas, because this will cover our whole set M, topological space M, which is locally homeomorphic to R. Hence this set, that is the line with two origins, is an example of a non-Hausdorff topological space. Non-Hausdorff one-dimensional manifold. This was all about the line with the two origins and the condition which we require, which we define in the construction of a topological manifold, that it should be a Hausdorff. This is not a necessary condition for a topological manifold. That is, we can drop this Hausdorff conditions. But why we need this Hausdorffness? This is obvious for some reasons, because in Hausdorff spaces, when we do analysis on a manifold, we want that our sequences must converge to a unique point. Otherwise, if a sequence will converge to more than one point, that will not be useful. That seems quite not good. Therefore, we want our spaces to be Hausdorff in order to have unique limits, and also for some other various reasons, because all of our metric spaces are Hausdorff. It is a nice condition in order to do analysis. Therefore, we need this. We require this condition, Hausdorffness, although it is not necessary. Thank you.